In this section, we're interested in finding the area between two curves, f of x and g of x. I've gone ahead and shown you a sample here where the parabola is f of x equals 9 minus x squared, and the line is g of x equals x plus 2. What we're going to do is we're going to find the area under each curve separately and then combine those answers together to find the area of the region that I see here. So let's start by finding the area under the curve 9 minus x squared between minus 1 and 1 down to the x-axis. So this is simply the definite integral from minus 1 to 1 of the quantity 9 minus x squared dx. To go ahead and find that exact area, what I'm going to do is I'm going to use the fundamental theorem of calculus. So I'm going to find the antiderivative of 9 minus x squared and then put in 1, put in minus 1, and subtract the results. So the antiderivative of 9 is 9x. The antiderivative of x squared is x cubed over 3. So in order for me to get the exact area here, I need to evaluate this antiderivative at 1 and negative 1 and then subtract the results. So I get 9 minus 1/3, and I'm going to subtract the quantity minus 9 minus negative 1 cubed over 3. When I put those together, I get 26/3 minus negative 26/3, and that gives me a total of 52/3. So the area that I see here is 52/3. If you look at the curve x plus 2, the area under that curve from minus 1 to 1 is simply the definite integral from negative 1 to 1 of x plus 2 dx. The antiderivative of x plus 2 is x squared over 2 plus 2x, and now I'm going to evaluate that at 1 and negative 1 and subtract the results. So when I plug in 1, I get a half plus 2, and I'm going to subtract what I get when I put negative 1 in, which is negative 1 squared divided by 2 plus negative 2. Simplifying that gives me 5 halves minus negative 3 halves, or 4. So the area that I see right here is an area of 4. To figure out what the area is that's enclosed between those two curves, I'll take the area that I got under f of x, which includes all the way down to the x-axis, and then I'll subtract out the section that was under the line. So when I do that, I get 52/3 minus 4, which gives me 40/3. So the area of the region between those is 40/3. So what I did here is I took advantage of the fact that I could find areas down to the x-axis, and by subtracting out the chunk that I saw down here, I could go ahead and figure out exactly what the area was enclosed between the two curves. So in general, this is a process that works fairly well. If f and g are continuous functions and f of x is greater than or equal to g of x on the closed interval from a to b, then the area between the curves f of x and g of x from x equals a to x equals b is given by the definite integral from a to b of the quantity f of x minus g of x dx. So what we're doing here is instead of finding the individual areas and then subtracting them, we're subtracting the functions first and then going ahead and finding the area. Notice that f of x, the bigger function, always has to come first to make sure that we get a positive area. So let's try that for the example that we just did. So f of x and g of x were the parabola and the line. So I'm going to do the definite integral from negative 1 to 1 of 9 minus x squared subtract x plus 2. Notice that since these functions have more than one term, I'm going to go ahead and write out these with parentheses. I can certainly go ahead and distribute that negative when I remove my parentheses, and what I get is 9 minus 2, or 7, minus x squared minus x, which gives me minus x squared. To be able to go ahead and evaluate that definite integral, I need to have the antiderivative of 7 minus x squared, and then I'll evaluate it at 1 and negative 1 and subtract the results. So the antiderivative is 7x minus x squared over 2 minus x cubed over 3. I'll put in 1 and negative 1, and that gives me the quantity 7 minus a half minus 1/3. Subtract the quantity negative 7 minus a half, subtract negative 1/3. When I combine my terms together, I get 37/6 minus negative 43/6. And when I put that together, I get 40/3. The exact same answer that I got before when I did the areas separately and then subtracted them. So you have the option of finding each of the areas individually or subtract, or take the functions and subtract them and then do the area. It doesn't matter which one you do. Let's take a look at using this idea to find the area of the region bounded by y equals x squared and y equals x. To get us started, we should go ahead and graph those two curves and see what we see. So here I see the line y equals x, and I see the curve y equals x squared, so the area that I'm looking for is the area between those curves. And the first thing I need to do is find out where these 2 points are. So these points of intersection look like they're at 0 and 1, but I better verify that to make sure. To find where those 2 curves intersect, I'm going to set x squared equal to x. So to solve this, I'm going to subtract x from both sides. That leaves me with x squared minus x equals 0. And now I'm going to notice that there's a common x in each one of these terms. I'll factor it out to give me x times the quantity x minus 1 equals 0. Setting each one of these factors equal to 0 gives me x equals 0 and x equals 1. And those are the 2 points that I found from my graph. So now I need to go ahead and subtract those 2 functions. I have to take the larger minus the smaller, and then I'll do the definite integral from 0 to 1. So the function that I'm going to have in front is the x, and the g of x, the smaller one, is going to be the x squared, and I'm going to be going from 0 to 1. So here's my definite integral from 0 to 1 of the quantity x minus x squared dx. I'll find the antiderivative and then evaluate it at 0 and 1 and apply the fundamental theorem of calculus. So the antiderivative of x is x squared over 2. The antiderivative of x squared is x cubed over 3. And I'll evaluate that from 0 to 1. So when I put 1 into these 2 terms, I get a half minus a third. When I put in 0 into each one of these terms, I get 0. So a half minus a third is 1/6. So the area between those 2 curves is 1/6. And that kind of makes sense because if you look at the picture closely, the area certainly couldn't have been more than 1, because a box that's 1 by 1 would have easily been way more than the area that was shown there. And so we got a number less than 1, so that's good.